For those of you who are new here, Space Drafts is part of an international network of Astronomy on Tap events, where we astronomers share fun astronomy facts with you and the rest of the public around the world. As you may have noticed a few minutes ago, we are right next to a live train track, and as I'm sure you all experience, you can't hear over it. So if a train comes through and makes the speaker completely inaudible, we have a tradition here at Space Drafts where if it comes by, blows its horn, what do? Raise our glasses and give it a toast. Say choo-choo. Hopefully that will not happen too many times, but just in case. So the format for tonight's show is going to be two speakers. Hello, fun sounds. There's going to be two speakers, each giving a 20 to 30 minute talk. In each of their talks, there should be at least one trivia question, perhaps more. One trivia question. So when that comes up, feel free to raise your hands. The speaker will call on you, and if you get it right, you can come up during intermission or after the show and come claim your prize, which will be one free Space Drafts sticker or merch of comparable value. Am I missing anything? Because my list is currently on the table. I think we are good. So without further ado, I will introduce our first speaker of tonight, Steward Observatory graduate student Jasmin Washington, who is going to tell us about physics in the Mass Effect video game universe.
Woo! Yeah. There we go.
Thank you, everyone. Okay, good. I'm not like screaming into the microphone. It's off to a good start. So, hi, as Lily said, and you'll hear now again, I'm Jasmin Washington. I'm a fourth-year PhD student here, and as your intro physics teacher would say, it is Mass Effect, not Wait Effect. So, before we get into it, and I will explain it for anyone who thinks that I'm just talking gibberish, who has played Mass Effect before? Raise your hand. Okay, about what I expected. Now, if you have played before, what class do you play as? Scream it out.
Soldier.
Infiltrator!
Yeah, Infiltrator! Woo! Okay, that's one of the ones I play. I respect you. So, alright. So, a little bit more about me. I am a fourth-year PhD student at Steward Observatory. I have not canned it yet. That's besides the point. Don't focus on that. I work with the Event Horizon Telescope collaboration. They made beautiful black hole images, not featuring my face, such as this one. And I specifically work on light curves for our central supermassive black hole, Sagittarius A star. Light curves is just basically how bright it is over the course of the night. As for my Mass Effect experience, I have played through the full trilogy 6 times with 2 different Shepherds. 3 different Shepherds, actually. I loved that game in high school. And I've played the 4th game once. Infiltrator and then Engineer are my favorite classes, and I made abundant fan art in high school, which I will now show to you to show off my artistic prowess. Just kidding, I literally threw away the notebooks last month and you will never see them. I never want to see them again. Those are embarrassing. But anyway, so now these will all be very dusty, and it looks like I'm giving a lecture. I promise I'm not. So we'll be talking about sort of history, and I normally see the slides here, so I'm going to get dangerously close and try not to die. The Drake equation, exoplanets and the star systems that they are within, a little bit briefly about extragalactic, and then also black holes, which is closest to my research. And for physics, faster than light travel, and then also dark energy briefly, and then this isn't physics, really, maybe PChem if you stretch it. It's just about a specific element made for the video game universe, element 0. And this is actually a mass relay. Mass is a very popular word in this video game series. So, for those who don't know, what is Mass Effect? So, in the year... Oh, that's loud. Wow. Okay. So, in the year 2148, and this is how the first game starts, in the year 2148, explorers on Mars discovered the remains of an ancient spacefaring civilization. In the decades that followed, these mysterious artifacts revealed startling new technologies. Enabling travel to the furthest stars. The basis for this incredible technology, thank you, was a force that controlled the very fabric of space and time. They called it the greatest, oh yeah, good, time for this move. They called it the greatest discovery in human history. The civilizations of the galaxy call it Mass Effect. So, this is a fictional video game series, but there are a couple ties to reality. So, while we have not found alien ruins on Mars, maybe in 2148 like happens in game, it reminded me a little bit of like the canals that were on Mars, and then there's like that whole thing of like, oh, maybe there's aliens. Not yet, at least. So, another thing is the character you play as in the trilogy, Commander Shepard, is named after Alan Shepard, who was the first American in space. And third, which isn't really history, it is unfortunately reality. In like a random conversation, someone mentions that their parents' house became beachfront property due to the rise in sea levels, and how many are breathe nitrogen and oxygen like us. There's also differing levels of gravity, which affects the builds of the different species, different atmospheric pressures, and then you also have actually two types of life forms that process different proteins, and if they were to eat each other's food, you could die, which is fun. And then, yeah, so I found this picture, and it's sort of just the different homeworlds for some of the different species. So this is Asari, and then humans, obviously, because it's Earth. Solarians, Turians, I don't know this one, I also don't know this one. Corians, Krogan, also don't know this one. This is the Elcor, and then this is the Volus. So now we'll move a little further out into the star systems that contain these planets. So there's at least 30 explorable within the original trilogy. I tried finding the exact number, and it was too many, like, overlapping, I just gave up after about 2 minutes. So there's different central objects within these systems. So there's, like, the typical, like, you have, like, a hydrogen fusing star in the middle. There's one where it's a hydrogen fusing star and then actually a brown dwarf, so fusing deuterium. One where the black hole is the center, like an interstellar. And then, yeah, so there's a lot of diversity, and some of them are actually, like, named or, like, modeled after real parts of the Milky Way, like the Horsehead Nebula. However, the systems within this Horsehead Nebula are fake. Other ones are the Arcturus cluster, and then also the outer rim of our Milky Way. Alright, so zooming even further out, moving to extragalactic very briefly. You would think, oh, it's WST era, we should talk about extragalactic. There's not much. So the latest game within the series is Mass Effect Andromeda. It was not as well received as its predecessors. However, it does still boast beautiful world design and deep lore. We won't talk about anything else. If you want to talk about offline, we can chat. So moving on to my research, roughly, black holes. So this is from Andromeda, and you have a system where a correct curved black hole is actually at the center of the system. And then moving to our central galactic supermassive black hole, Sagittarius A star, Sag A star for short, we have this, it's actually a destination in the second game. So mainstream science would have you believe that this image provided in 2022 by the Event Horizon Telescope is the first image of our galactic black hole. However, those who are faithful to the Mass Effect science would tell you that it came out in 2010 with Mass Effect 2. And you looked at it this whole time, that's correct, it was the title image. I did trick you and you didn't even know it. So what is really around Sag A star? So many would have you believe it's hydrogen gas mostly, but it's actually a collector base and then some ships that got busted up by the black hole orbiting around, and I think possibly as resolution for the... Can you guys hear me still? Fantastic. I believe maybe as EHT resolution increases, we might be able to see this space, but for now we need to hold off. And you might wonder, how does an alien base survive so close to a black hole? And the explanation, very thorough, something about Reapers, something else. I have no idea. They didn't either. So now we cut to my sponsor for this talk, Element Zero. So if you need to fill a gap in your science fiction plot, Element Zero is your go-to guy. So do you need artificial gravity in your ship? Element Zero. Do you need high-strength construction materials? Element Zero. Do you need to travel faster than light? Element Zero. And now say it with me, everyone. Do you need your species to contact other species?
Element Zero.
Heck yeah. That was not close. So disclaimer, Element Zero cannot be used as a true weight loss supplement, as that depends on your gravitational constant. So how do we use this dark energy to fill our little plot holes? So it turns out, and I forgot to mention, Element Zero is generated when a planet, and Jeniveve, you'll love this one, when a planet is affected by a supernova explosion or any other solid matter, Element Zero is generated. How? Don't ask me. That's not important. But if you run an electrical current through it, it generates a mass effect field, because dark energy is released, and then this dark energy can obviously be manipulated into a mass effect field, which affects, as you might guess, affects the massive objects within the field. If you run a positive current, your mass increases. This is how you get your artificial gravity in ships. Don't ask me how they distribute it so perfectly to let you run around. If you run a negative current, it's decreased mass. Very simple stuff we're talking about here. So that's how you can travel faster than light. And so to conclude, let's do just a little bit of math. So how fast are we talking? How much are these ships just zooting through the universe? So I did research by playing the game a little bit recently, and a typical loading screen time for a mass relay was about 8 seconds. For simplicity, we'll say the shortest distance you travel is 8,000 light years, and the longest distance is about 80,000 light years. So this breaks down to 1 times 10 to the 19 to 1 times 10 to the 20 meters per second, which I realize means absolutely nothing. Speed of light is roughly 3 times 10 to the 8 meters per second. And so, in short, it's about 100 billion to 1 trillion times the speed of light that these ships are just blasting. So, in short, those ships are rolling. Yeah. So in conclusion, as you guessed by me rambling, Mass Effect has an in-depth and diverse imagining of what sort of humanity's future could look like, maybe, and also potential existence of extraterrestrial life and how it might vary throughout our own galaxy, and perhaps even other ones. And so I have simply scratched the surface. There's so much I did not cover here that is within the games, and there's even books and stuff. So if you want to procrastinate, want to take a lot of time, want to get really into something, highly recommend Mass Effect. If you have any questions or comments, please feel free to contact me either during a break or email me at Washington, as in the first president of the United States, J at Arizona, as in our state, .edu. And if you want to debate anything I said in my presentation or my player class choices, we can meet in the parking lot after this, or you can come up to me during a break. Either one works. And finally, thank you to everyone for listening to me use the time I spent playing video games in high school, finally put it to use, and my family who is attending on the East Coast virtually, and also my husband for wearing a jacket in extremely hot weather, just because it's Mass Effect themed. And thank you, everyone. Alright. The light is hitting the mists, so if anyone has any questions, it might take me a hot minute to spot you. I apologize. Yes.
Can I play this on the Xbox?
Yes. So there's
Can you repeat the question?
Huh?
Can you repeat the question?
Oh, so the question is, can you play this on Xbox? So they recently released Mass Effect Legendary Edition, which is all 3 games in the trilogy for only like $20, I think. It's a really good deal. I bought it, and I have grad school income. So yes, you can play it on Xbox and also PlayStation and PC. Thank you for your question. Anyone else? Oh, yes, Jeniveve.
Do you have a favorite planet in Mass Effect?
Ooh, tough question. Oh yeah. Thank you, Lily. So the question was, do I have a favorite planet? I would say probably. Yeah, I would say probably the Korean homeworld. It's really pretty, and there was no one on it for a while, so that's probably why it looked so pretty. Person in the back. Or was there a question? Matt, I'm sorry.
What's your favorite alien species?
Oh, my favorite alien species. My favorite alien species would definitely have to be, I would say, I really like how just circular the Volus are. Yeah. Anyone else? Okay. Thank you.
Thank you very much, Jasmin. I have never played Mass Effect, and I do not play videos, but perhaps I will start. So, we will now be having a 20-minute intermission. It is now 7:56, so let's just call it 8:15. Feel free to come. We have a merch table over here, so feel free to come talk to us, chat with speakers. Whoever it was who won the trivia question, please come let us know, and you can pick out your prize. When you go inside, make sure to please tip your bartender. And I think that is about it for now. So see you all again in 20 minutes for our second talk by Jeniveve. Do we need a gigantic more pile of...
I cannot use my touchpad because it's getting...
I'll go source.
your, hopefully, chance to get a drink, take a bathroom break. Yes? So up next we have Jeniveve Pearson, who is also a graduate student at Steward Observatory, who will be telling us the life story of a massive star.
Yes, I need the clicker. All right. Hello, everybody. My name is Jeniveve Pearson. I'm going into a fourth year PhD student at Steward Observatory. And as Jasmin so helpfully mentioned during her talk, I study supernova. So today, I'm going to tell you about massive stars. Choo-choo! So before I begin, there's one important thing you need to know about me, and that is that instead of being obsessed with video games as a kid, I was obsessed with fairy tales. So hence, we're going to do a fairy tale retelling of the life of a massive star. Alrighty. So we begin. Once upon a time, in a galaxy much like our own, there was a cloud. Now you may be saying, Jeniveve, you promised me stars. That is a cloud. Much worse, it's a pretty ugly cloud. You might be used to it looking more like this. This is that J2ST image that came out recently, I guess last year now. But here we have our humble cloud. And this cloud, this molecular cloud, is made up of primarily molecular hydrogen. Can you guys hear me? Okay. I can barely hear myself, so just want to make sure you can hear me. All right, it's made of mostly molecular hydrogen, and it's pretty cold. It's about 10 degrees Kelvin. For those of you who have no idea what Kelvin is, that's minus 442 degrees Fahrenheit. This is the only time I will show you Fahrenheit during this talk, because it is the only time in which it matters. Everything else is just hot. So, this cloud has a density of about 100 particles per cubic centimeter. In comparison to space, which has about 1 particle per cubic centimeter, that's pretty dense. But in comparison to Earth, that's not dense at all. But we were comparing to space here, so it's a very dense cloud of dust. It's a big cloud, about 100 light years across. In reference, it takes 8 light minutes for, the distance between Earth and the sun is 8 light minutes. So it takes 8 minutes for light to come from the sun to Earth. So this is a long distance, pretty big cloud. And there's a lot of mass in this cloud. There's 1 million times the mass of the sun worth of dust and molecular gas in this cloud. So now if we zoom in, we can start to see some structure in this cloud. I'm not sure how well you can see the structure in the back with all the mist, but it's there, I promise. We zoom in even further, and there's this slight darkness in the center. And this darkness here is called a Bok globule. And it's named after Bart Bok, who was the astronomer who discovered these. And he referred to them as these like cocoons of star formation, these dense areas of nebular clouds where a star forms. Now you might know the name Bart Bok, and that's because the Bok 90-inch telescope up on Kitt Peak is named after Bart Bok, and that coincidentally is the telescope I most often observe at. So here we have our globule, and it's more dense than the rest of the cloud around it. But as we all know, things that are in motion stay in motion, which means that things that are not in motion stay not in motion. And so this cloud will just continue to be a dark little void of lots and lots of particles. Unless something gives it a little kick. So we get a little kick from somewhere. I won't go into where just yet. And this causes the cloud to start to come together. And slowly, all of these particles come towards a point, because now gravity has, their equilibrium has been upset, and gravity is pulling them down together, because we have this dense region. And as these particles come closer and closer together, they start slamming into each other, and that creates some motion in the gas, which heats the gas, and ultimately causes it to become regular hydrogen instead of molecular hydrogen. And this process continues for a while until eventually we form, where's it gonna go? A protostar. So here's our little protostar. We have to give them a name. We can't have a star without a name, so somebody yell out a name. Henry, all right. So this is Henry. They will continue to be in the protostar phase for about 60,000 years and slowly coalesce until eventually 60,000 years later, they start burning hydrogen in the center of the star and begin their journey on the main sequence. So the main sequence is where stars burn hydrogen in their cores into helium. I'll talk a little bit more about that in just a second. But you'll notice there's still this red haze around Henry. And that's because all of the mass that makes up Henry isn't in Henry yet. He's still a growing boy. And that's because you don't need all of the mass that ultimately would be Henry to make the core hot enough for him to start burning hydrogen into helium. So, this material around him will slowly accrete onto him in the beginning of the main sequence until eventually he looks like this beautiful O star right here. So this is Henry in his final form for now, his final main sequence form. He is 15 times the mass of the sun, and with a radius about 7 times that of the sun. So a big boy, a little happy guy. And so I'm gonna run through some quick facts about Henry. Most important fact about Henry, that he's a rock star, all right? First thing you learn about rock stars is that they live hard and die young. And Henry is only gonna live 11 million years. Now, to you and I, who live maybe 100, that's a long time. But the sun, good old trusty the sun, will live 10 billion years. So Henry's gonna die pretty young. Another thing about rock stars is that they're hot. Henry is 5 times hotter than the sun at a nice smoking 28,000 Kelvin during his main sequence. And rock stars are glamorous. And indeed, this rock star is 17,000 times brighter than the sun. So truly, a rock star. So, I'm gonna pose to you a hypothetical. This is not the trivia question, don't get your hopes up quite yet. We have all had that 3-year-old in our lives who wants to know why, and the dreaded question of why. So here is the first question the 3-year-old asks you. Why do stars shine? Does anyone want to yell out an idea? What? Fusion. That is not correct. Stars do not shine because of fusion. Because they're hot. Stars shine because they're hot. Okay, now, in classic 3-year-old fashion, they ask you, but why are stars hot? Anyone want to know why stars are hot? No, it's not fusion. Anybody? Pressure? Close. Gravity. Stars are hot because they are trying, we have all this material trying to go to a point, which, like that cloud, is causing all these thermal motions, and that they're hot because of gravity. So now the question really is, if there's gravity, why don't they just collapse? Okay, so now you all have said this answer, so what's the answer to this? Fusion! Fusion! So, Here is a little cross-section of Henry on the main sequence. Henry is burning hydrogen into helium, and that helium is being in the core of the star, and so that we're depositing like a little tiny core of helium in the center. Henry does this process via something called the CNO cycle, which is a little different than how the sun burns hydrogen. So in the sun right now, you're basically smashing together hydrogen particles and to create helium. Basically just smashing it together, and that process releases energy. But with Henry, he's a little bit smarter. He is smashing his hydrogen particles into carbon, nitrogen, and oxygen, and that ultimately produces helium, but it also produces a lot of energy. And it produces much more energy, much more efficiently than the sun. So he will burn through his fuel and be much brighter than the sun, much faster, even though he has a lot of fuel. So he will be on the main sequence for about 10 million years. Now, if you remember, his entire life is 11 million years, so this is the vast majority of his life. Once he comes off of the main sequence, and he burns enough helium in the core so that helium can also ignite and start burning, he turns into a red supergiant. Now, Henry has changed a little bit. He's a little cooler, 4,000 degrees Kelvin, and he's a lot bigger. We are talking about 1,000 times the radius of the sun, so a lot bigger. Now, before I continue on the story of Henry, we must take a step back briefly, because I wasn't entirely honest with you when I started. Here's that globule, that Bach globule that condensed into Henry, but there's one right next to it. And that globule will also condense into a star. So we got a little extra little sibling star right here. What is the sibling named? Anybody? Joy. Joy? All right. So we got Joy and Henry, little family portrait there. They're so cute and so adorable. How many, now here's the trivia question. What percentage of massive stars like Henry have companions? Is it A, 15%, B, 33%, C, 50%, D, 70%, or E, 110%? Whoa. Raise hands. In the back. 70%. You're correct. 70%. So that means most stars like Henry have a little Joy with them. Now, show of hands, who has siblings? Yeah. Okay, so we need to talk a little bit about the behavior of siblings. Namely, two main things that are of importance here. One, siblings invade each other's personal space. And two, they like to borrow. Okay? I like a brief anecdote here. I have two younger sisters. My middle sister, when they were younger, used to steal my youngest sister's French fries from her dinner plate. And when she was confronted as to why she was stealing my littlest sister's food, she said, well, if she didn't want me to take it, she shouldn't have put it right in front of me. And that is kind of what's happening here with Henry and Joy. So you have Henry, he's in his main sequence phase, 7 times the radius of the sun, a big boy, but not taking up too much space. And then he suddenly decides to go and puff up. And now he's a little bit in Joy's space. And now, can you really blame her for just taking a little off the top? Okay. So Joy here, she takes a little of the mass that belongs to Henry, and ultimately grows a little bigger. Now this mass might wind up enriching Joy and extending their lifetime, which would be great for Joy. And Henry won't notice a difference because he's not burning that material anyways. Well, he's burning it, but it's not contributing to his lifetime. So he's got lost a little bit of his hydrogen, but ultimately, who cares? He could use some slimming down. So Here's what Henry looks like now, towards the end of his red supergiant phase. He has this growing helium that he's burning slowly and into carbon. And that red supergiant phase, this helium burning phase, will last about 1 million years. So 1 million years of joy stealing from Henry. And then that helium is being burned into carbon. And that carbon eventually will get hot enough so that it can burn, and that will burn for about 1,000 years. The carbon will burn into neon, and that neon will burn for about a year. That neon burns into oxygen, which will burn for about a year. You might notice we're getting a little shorter here. It's coming to a close. The oxygen will burn into silicon, and silicon will only burn for about a day. And silicon burns into iron peak elements. So we have iron here. And iron is a special element in that it is one of the elements you cannot get energy from if you do fission on it, like split it apart. It takes energy from the environment to do that, and it doesn't deposit any energy. And if you try to do fusion, slam it together, it takes energy away from the environment as well. So we have a problem. Henry has been producing this energy in the center of the star in order to counteract the gravity of the star, coming in, trying to collapse into a point. But now the iron is helping the gravity and not counteracting it. It's taking energy away from the star. So the iron will burn for about a second before Henry has to sing one final song, one last hurrah to show the millions, the multitudes, the rock star he truly is. This supernova that Henry has produced is 2 times the energy the sun will produce in its entire lifetime. 10 billion years of the sun's light, of the sun's energy, and Henry just did that in under a second. That explosion is as bright as the entire host galaxy which Henry resides in. So truly, a fitting ending for a rock star. Now you might be wondering, oh my God, what about Joy? No worries. They're on an adventure to see the world, to see the universe. And they'll go off into space and have an exciting time. Now, I said at the beginning, this is a fairy tale retelling. Fairy tales always have a happy ending. And Jeniveve, you've just killed off the hero. That is not a happy ending. Relax. He's not dead. He's just a little smaller. This is Henry now, the neutron star. He is 1 million degrees Kelvin, hotter than he has ever been in his entire life. And he is only about 20 kilometers in diameter. For reference, that is 12.4 miles. You could run from one side of Henry to the other, though I do not recommend it. And because he's the mass, a little bit greater than the mass of the sun, he's incredibly dense. The density of Henry is about 10 to the 15 grams per cubic centimeter. For reference, lead, which is one of the heaviest things we can think of, is only 11 grams per cubic centimeter. So, significantly denser than lead. And so, okay, now what happens to Henry? He was this great rock star who created an explosion that will be seen from multitudes and multitudes of galaxies. Well, he's retired. he's going to sit there and he's going to cool off for a couple billion years. And that's all he's going to do. He's vibing now. Now the shock wave that his supernova produced will continue to go propagate through the cloud that he was once birthed in and create a little kick that might start star formation elsewhere in the cloud, producing other Henrys and Joys. Every good story has an epilogue, and our epilogue begins millions and millions of years later, on a Friday afternoon, when all of the supernova people at Arizona are dropping everything to observe everything nearby. And here, this right here, is supernova 2023 IXF, which you might have all heard about in the news recently. It's in the Pinwheel Galaxy, and it was super exciting because it's the nearest supernova in a decade. And so we all dropped everything to observe it. Now, we don't know precisely what the progenitor of 23 IXF is, but it's probable that it was something kind of like Henry. So, whoever watched Henry's supernova is probably up in the middle of the night trying to get a paper finished right now. So, that's the end of our story. Thank you all for listening. I'll take any questions. Lisa.
So, why it's most likely for the stars to have companion during formation?
I'm sorry, what?
Why it's most likely, you said 70%, for the stars to have companion during the formation process?
So the question is, why is it likely for massive stars to have companions? And we don't actually know that for sure. It's an observational thing that we have observed. But it's thought that maybe we have these huge clouds that are coalescing, and so they're fragmenting pretty easily. And so you get smaller clumps that form into smaller stars. Other questions?
Question from the chat.
Yes.
Question from the chat from Chris. If the dust cloud was 100 light years wide, how does it coalesce in only 60,000 years into 7 times the size of our sun?
So the question is, if the cloud is 100 light years wide, how is it coalescing into this object in 60,000 years? So one, I didn't tell you how long it took for it to coalesce into a protostar. I only told you how long the protostar takes to get to a Milky Way, to do the main sequence, sorry. And it takes quite a long time for a cloud, once it's been kicked, to collapse into a protostar. That being said, the entire cloud is not forming one star. That would be a very big star. Like I said, that the mass of that cloud is 1 million times the mass of the sun. So it's only like a dense region in that cloud, like one globule that forms into the massive star. Anybody else? Yeah, so the question is, what starts the fusion process? So fusion occurs, basically, you have the random motions of the particles in the center, and so the hotter it is, the more likely those particles are to smash into each other, and the more likely they are to fuse, instead of just ricocheting off of each other. So it's a very temperature-dependent process. It relies mostly on temperature. So the hotter it is, there's like literally a line, whereas if the temperature is above that, it's it's fusing, but if the temperature's below that, it's not. So you literally have to, the gravity is causing everything to heat up, and then eventually the center is hot enough to begin diffusing helium, and then you create your helium, and that helium gets denser and denser and denser until the center is hot enough to begin fusing helium, and so on and so on and so on. All right. Nobody else?
When do we get Joy's story?
Joy, yes. Well, I didn't give Joy a mass. I like to think Joy is about the size of the sun. So maybe somebody will give you Joy's story in the nearby future. Joy does not produce a supernova, though. So there you go. All right. Thank you so much.
Thank you so much, Genevieve, for that incredibly riveting fairy tale. And thank you all for joining us tonight for Space Drafts in this incredible 100-degree weather. So next month, we normally have our shows on the second Tuesday of every month. Next month will be a little bit different. We will be out here on August 8th because the Rubin Observatory, which you may have heard of, is having a meeting in Tucson. So we will be having something of a Rubin-focused show next month, again, August 8th, which is probably the first Tuesday, not the second. So please come join us for that. Otherwise, thank you all again for joining us. We will still be out here with our merch table. Tip your bartenders on your way out, and thank you again.